basically, we got this suit last year, and this suit serves two purposes. One is to evaluate how adequate is the soft suit for surface EVA capability. The other one is to evaluate suit port concept. Does anyone know what a suit port is? A few people. So basically, typically when you go EVA, either depress your entire cabin or your vehicle or whatever else. Or if you have a big enough vehicle, you have an airlock. You get to that, you don a suit, you depress the airlock, you go out, and then you go in reverse. So there's a lot of logistical overhead associated with that. There's potential consumables loss associated with that. And if you're on the moon or the Mars, then you have to deal with the dust you're bringing in. So there's been a concept called suit port. It's been around for quite a while, 20 years or so, where basically you have the suit that's kind of hanging off the outside of the vehicle or the habitat or the rover. And it's at the same pressure as your habitat. So what you do is basically just open up a little door, you climb into the suit to the back, you step off the vehicle, and then you're EVA. So it's a really attractive concept. But there's also a lot of things we don't know about it and potential issues we have to resolve. Such as how is donning a suit? How is getting into a suit when it's pressurized? How does that work? Or how do you make sure you have good fit on your boots and your gloves? How do you perform maintenance? Things like that. So we've had an interesting experience with this suit. Kind of as an aside, when I was working in Constellation, we made, but on the suit side, constructed 6 or 7 prototype suits of comparable fidelity to this suit. Yet the amount of media that's covered on this suit is probably an order of magnitude more than all the other ones combined. So I definitely know that this helped. And I've seen we got a lot of good press. Time Magazine named us top 25 inventions of last year. Top Gear was out a couple weeks ago and shot a thing on the suit. Well, we've also gotten a lot of kind of negative press and negative comments. A lot of armchair engineers and people on blogs being like, there are all these people writing these articles, and they would say, this is NASA's new suit. So you can't really blame people when they see an article that shows this picture here and says NASA's new suit, and they come away with the impression that this is something that we're flying next year. So just, in general, kind of the importance of properly communicating the fidelity and the purpose of the hardware that you're building. So in our case, it's not, it is our new suit, but moreover, it's a prototype. It's a developmental platform that we're going to iterate several times, and we're just kind of exploring the design space, so to speak. So the other thing that's interesting that I've learned about this suit is the cover layer of the suit serves two purposes on a suit of this fidelity. One is to hide the technical design of the suit. The specific technical design is not export control approved. You have to cover it up. And then also just for testing and evaluations, it provides abrasion protection and things like that. So, when we go and write requirements for the cover layer of a suit like this, we're like, it shall have one. You don't really care about what it looks like, so to speak. But moving forward, I think we want to think a little bit more about the aesthetics of the cover layer and what it looks like, because the better publicity you get, the more attention it gets, the more money you get, and it kind of is a cycle. So suit design, but it's still something that's worth mentioning. Or half of everything else that we're doing. We're doing a lot of the Z1 suit evaluations. So we tested the suit port concept in the vacuum chamber. We did a reduced gravity flight last year against another suit in Lunar and Martian G. We're doing a lot of improvements in the glove to try to improve the mobility and the durability there. One of the things that we don't know about is we understand how the suit moves when a person's in it, right? We can do evaluations, and there's different ways of assessing the mobility of the suit. But what we don't really understand is how a person is moving inside the suit, how a person interacts with the suit, where it's coming into contact with how much pressure and when. So that's one of the things we're currently looking into, advanced sensor technology that enables to understand that interface. Generic interface stuff, like integrating this hardware, improving fidelity, increasing fidelity, just paying attention to what are our interfaces. And then the next iteration of our suit is Z2, aptly named, and the procurement actually should be awarded today or tomorrow, I think. So that's the kind of next iteration, and we're trying to grasp. Can we get that suit? What are we going to be doing with it? What lessons do we need to learn for the next round? So it's kind of what we're doing. So basics of suit design. The goals of spacesuit are pretty simple. You want to basically protect the suit from what's outside, whether it's a vacuum environment or a thermal environment. Dust, if you're somewhere that has dust. And provide the mobility and the comfort for the tasks you need to do. That's basically the long and short of it. In terms of construction, you kind of have a wide range. There's a really big design space. You have your hard suits that are completely hard. Hard components are pretty easy to understand. You can perform stress analysis on them. You can do a lot of different things to understand how they work and what your design is like. On the other side is the soft suits, and that's much more of an art form. It's not something that we can currently model. Pressurized soft goods is not something that we can currently model at all. And in reality, most suits fall somewhere in between on that spectrum. There's very few all soft suits. There's very, very few all hard suits, and there's usually somewhere in between.
What do you mean by you can't model it? What are you modeling with the suit? Like actually building?
So like if I wanted to design a suit in Pro Engineer with soft cloth that I inflated and moved, there's currently no tool available that can understand the stresses and the loads that are going on and say, yes, we're okay. And then suitability, what are the needs and the requirements for the mission? An IVA suit and an EVA suit are very different design drivers, very different needs, and therefore very different suit architectures. So I like to always throw the glove up first because it's kind of like a microcosm of the whole suit. You have a lot of joints of varying degrees of freedom in a small amount of space. You're using them all the time. And in terms of what's on the suit now, it's the most recently updated and most frequently updated component. So we basically have 3 layers to a suit. And we can go back one. You have a bladder layer, and that's what holds the air. That's the gas container. But just like any balloon, if you want to inflate a balloon, it wants to go to a sphere. So you have to basically hold the shape. And to hold the shape and carry the load, you use the restraint layer. And those are the 2 primary layers of the suit. And then, based off what the intent of your suit is, you have a cover layer. And that is either just to provide basic abrasion protection and cover, or it's to, if you're doing an EVA, thermal protection, micrometeor protection, things like that. So on the Phase 6 glove, which is the glove we're currently flying, you first have your bladder layer, and that is a dipped urethane material, and it's flocked with cotton, so that's like a light cotton flocking. And I have one of these today. I'll pass it around in a couple minutes. Then you have your restraint layer, so that's shown here in the back, here in the front, and that's the dorsal aspect of the ring finger thing. But here's where you see the money, so to speak. This is where a lot of design goes in. You can see all the patterning that's happening here, the pleating on the fingers, the patterning here at the thumb, sizing capability on the finger here. So you have these little keyhole brackets there that you can use to resize. So that's a better one there. We have gimbal rings here to allow for wrist mobility. One of the things, if you imagine taking a glove, I'm sure everyone's done it, when you take like a nitrile glove and you blow it up like a balloon, the palm, it balloons out. And that's a problem with gloves, is you lose the natural concavity of your hand when you pressurize them. And you're pressurizing suits to about 8 psi, between 4 and 8. A basketball is 8 psi. So when I say that the suit is soft, it's a soft material, but when you pressurize it, it's like hard like a basketball. So that's why there's a lot of effort that goes into designing these restraint layers. In any case, to hold the shape, we have a stainless steel palm bar that goes right there. And then we also have a palm plate, it's a composite material, and that kind of holds that shape so you can actually grasp stuff. And then lastly, the outer layer is the TMG layer, the thermal micrometeoroid garment. And this has 6 or 7, 8 layers in it. It has a Teflon material on the outside, as well as a orthofabric weave, which I'll talk about in a couple minutes. Dectran on the palms for abrasion protection, things like that. And it has aluminized mylar, several layers of it, 5 or 7 layers for thermal protection. So this is a fun slide I can put in here that kind of just shows the breadth of the design space of one joint. So these are all suits that are designed to be pressurized nominally, and you can see there's a pretty big difference in the different ways you can, skin the cat, so to speak. The ones up top are all considered soft joints. The ones in the bottom are all considered hard joints. So number 1 is what we call a patterned convolute joint. And it's exactly like it sounds like. It's a convolute that's made out of a bunch of pattern pieces. So each one of these little tiny strips is an individual pattern that's been sewed together, as well as this webbing. This has a side bearing, a shoulder bearing, as well as an upper arm bearing, but we still consider that to be a soft shoulder. I mentioned that the restraint carries a load, right? So the material here that we're using, which is a Dacron material, it's a basic polyester weave. This is designed to carry the hoop load. So when you want to inflate a balloon, it wants to balloon out, right, circumferentially. This material holds that load. But if you take one of those balloon animal things and you inflate it, it wants to also elongate axially. So we have to also have axial restraints. So here you can see there's an axial restraint cord that goes right there with brackets. And those are usually placed along the lines of non-extension of the suit, of the joint. So, when you're moving your joint, the inside of your joint changes and the outside of your joint changes through its range of motion in terms of the length. But the sides don't change very much at all. So we place those axial restraints along there. There's one on the front there, and there's one on the back that you can't see. That's a pattern convolute. Next one's a pattern gore. So this is on the current EMU that we're flying today. There's also a side bearing and an upper arm bearing. It's also patterned, but it's more similar to like the way a beach ball is patterned, how you can see how the flat patterns that form a sphere. More similar to that type of a pattern. What's interesting on this guy is that this is a flight suit. This is a prototype suit. You can see how much more robust the axial restraint line is on that versus this one. So that's kind of an interesting thing. Number 3 is from the Apollo suit. This is from the A7L suit. This is a molded. It has a cable assist feature. So you have a cable that's fixed here. It has a pulley that runs around the back, and then you have another bracket on your back side opposite of this one. This also has upper arm bearing. So there's some hard pieces in there, but again, it's considered a soft shoulder. Number 4 is an external link rolling convolute, which is one of my favorites. I think one of most favorites. It's really nice mobility. On this particular suit, you have a bearing on either side of it. This is a soft material, but since there's so many hard components, it's considered a hard shoulder. And I'll talk a little bit about this one on another slide when I get to the suit. Number 5 is just a random example I pulled out of an Apollo prototype suit. It's armored link convolute, similar to this guy. this is a spherical stovepipe joint. We don't see a lot of these very often at all. Mostly because you pay a huge mass penalty. This particular one, I think, is made out of solid aluminum, so the mobility is not that much better than something like this, or really something like this. So it's not something I've looked at recently, but it's certainly. Okay, so I'm going to get into the hardware, so I'm passing around. I think 3 rules in the hardware. If you guys could take off your rings, bracelets, and watches when you're holding the hardware, just put it on the table, that'd be great. Just to prevent snags and things like that. Yeah, no pizza grease in the hardware, like I just mentioned. And don't put the com cap, the Snoopy cap, on your head. You can, but if you get lice, don't blame me, because like 20 kids had it on, or hundreds of kids probably had it on in the last year. So this is a layup of the current EMU. The current EMU, when you get in, the first thing you wear is a thermal comfort undergarment, basically like long johns that you wear. And then on top of that, you have a liquid cooling ventilation garment, and I have one of those to show in a bit, but that's what carries air and cold water against your skin to cool you down. On that particular garment, you have this nylon chiffon, and then you have a stretchable nylon, aka spandex material woven with plastic tubing, and that's what cools you down. So you get that LCVG on. We'll see it here in a sec. On the suit itself, it all kind of comes as one assembly, but if you were to actually break it all out, the first layer is your bladder layer, it's your gas-containing layer. This is a polyurethane coated nylon, and you have the restraint layer, which is a Dacron, aka polyester. A lot of the suit materials either sound they sound a lot more exotic than they are. You know, like Dacron, what's that? Oh, it's polyester. You know, so. There's specific weaves and things, and there is a lot of thought that goes into it, but we're not using like crazy space-age materials most of the time. You know, we're using the same materials a lot of time that we've been using for decades and decades because they work. Most of the effort goes into the actual construction. Then you have your TMG layer, which I mentioned on the glove. You've got a neoprene-coated nylon stop, and that basically is your last protection if something cuts all the outer layers. This is the last thing that stops, supposed to stop it before you hit your restraint layer. Then you've got aluminized mylar. Mylar is polyester film, by the way, with Dacron scrim, also polyester. So it's like 5 or 7 layers of that, depending on where you are in the suit. That's for thermal protection. It also provides some commuter protection through some of the thin layers. And then you have a thing called ortho fabric. That's probably the most exotic material on the EMU layout. It's a weave of Kevlar, Nomex, and Teflon. And it's kind of cool. It like stretches in your hand and stuff. So that's that guy. So I'll pass that around here. And everything, there's no plastic tubing, but. So next I've got the lower arm segment. So this is from the current EMU, like I said, and lower arm, aka elbow. And here you can see that we have the bladder layer there, the restraint layer here. You can see this is the pattern bore construction. You have your axial restraints as well as your brackets that carry the load between hard components on either end of this guy. This is an older version of the arm, and I'll get into a little bit more about what that means, but this is a sizing panel here. Where you can, if you want to make this shorter, you pull out this whole lacing cord all the way on both sides, and take out the sizing strip and then put it back together. So that's this guy. So then I've got the upper leg or the knee. It's very similar to the elbow, single axis joints like the elbow and the knee are pretty easy to do. We haven't really spent much time or effort on them just because they're pretty easy. The soft ones that we have is the pattern gore and the pattern convolute we like. So, this is just a basic pattern gore, same thing, water restraint, axial restraints. There would be brackets here like the elbow, but it doesn't have it. Go past that guy around. So gloves. I have a few different gloves to pass around. Basically, I have two glove assemblies. The first one is the 4000 series glove. That's our older glove, and it comes as a full assembly in this particular instance. I've inverted the TMG so you can see the design details of the restraint layer. That's the old one. And then I have the new glove, which I showed in the previous slide, the Phase 6 glove we're flying today. And I have a bladder and the restraint and TMGs are separate. You can see when you get it in your hand, there's a lot of design differences that have happened here. The fingertips have been changed from a molded here to a more patterned low profile design. We added sizing on the fingers. We repatterned the thumb from this guy to that guy. We added the palm plate, the composite palm plate here in the middle. We have 2 gimbal rings instead of 1. The bladder in this guy is patterned. It's just a couple pieces that are sewn together. This one is dipped, so you get the advantage of these kind of convolutes in here that you don't have. So I will pass that around. So that one is the 4000, and then this is the Phase 6. Any questions so far? Yeah.
How do you put all this stuff together? You'll get into it later, but how are you actually sealing the body and the gloves and the arms?
I don't get too much into it. I can talk about it on the slide. It's probably better, but like in this particular instance, you have this bearing. What do you call it? Drawing a blank on the name. There's a bearing here at the wrist, and you have clamping rings that attach that bearing to the soft goods. So you clamp this down with the 20 screws with a certain torque, and then you might have another hard interface. So like when you put the gloves on, you have 2 hard pieces that clamp together, and they're dual sealed, and each one of those is clamped to the soft goods. And you can kind of just follow that whole method of construction of the body. So you have the same thing like when you have an arm bearing, same thing with the side bearing, same thing with the helmet. So we just kind of and then I'll get into the pressure sealing closure, but of course then you also have a means of getting in and out of the suit, right? So there's 3 primary methods. One is a body seal closure, where you basically same thing as this, where you have 2 metal rings that attach together, but it's like one at the waist, so it's a big body seal closure at the waist. We'll have a pressure sealing zipper, those are used pretty commonly, and then you have a rear entry hatch. Okay, other stuff that I'll start passing around here. Maximum absorbency garment. Hit with the kids, they love it. It's not used. I have a boot. I have a count cap assembly, CCA, safety cap. I have a wrist mirror, which you use to see the control in your chest, like this. Disposable in-suit drink bag, EIDB. Goes in your chest, carries water, so you can drink or EPA. This is a comfort glove made out of Spectra knit. It's kind of a weird material, but it basically just goes on your hand below the glove, and it's just for comfort and moisture. And then I have the liquid cooling ventilation garment, and that's the slides finished, it'll be the nylon chiffon and the spandex with the tubing in it. So you have all this tubing that runs through the whole suit that circulates water like 55 degrees or something, and it I'll put you down. It also has ventilation tubes, which are not in here right now. They suck air from your extremities. So you get air from the helmet, that's your positive side. On the negative side, where it's being sucked in is at your extremities. So you actually get decent ventilation through the suit. It's not just in the helmet, you're sitting there in your suit, like getting all hot and sweaty. So I'll pass this stuff around. Any questions I can answer while I'm doing that?
I think I believe it makes sense.
So we have made custom, okay. So the suit itself is pretty much modular, like it's designed to fit a certain angle range. And if you don't fit in the suit, then tough luck, but it's got a lot of types of capabilities. So there's only like one existing crew member who's too small for the suit. The gloves are all semi-custom. By that, when you get a new crew member, they come in and do a laser scan of their hand, and if they are close enough to an existing size that we've used before, then they use that. Otherwise, we generate a new size, and then that's their size. So like sometimes, crew member Bob will wear, crew size Joe glove. So back in Apollo, Mercury, Gemini, all of those were custom. But right, yeah, because I mean, there's definitely a trade that you have to make between how much money you want to spend on sizing, because you can make a suit that fits everyone and is readily sizable without tools and all these things that are great, versus how much money you want to spend on having custom sizes. So like back in Apollo and Gemini, when we only had a handful of astronauts, it made sense to custom. Now that we have many more, it just doesn't trade well. So that's one thing that we're looking at for things like Mars. If we're sending someone to Mars, for 2 years, and we're only sending 6 people, probably makes sense is to do custom for that. So there's a trade there. But on the EMU, it's not custom.
What is this one?
That's the wrist mirror. You hope you have it on your wrist and you can see your controls on your chest. Yeah.
Do you have any, in suits, is there any kind of built-in safety precaution for if it, it does have to be pressurized or anything like that? There's ribs, tears, whatever.
So it's designed, the suit's designed to protect against a certain size hole that I can't remember what it is, maybe like a 1/4 inch or something. Basically, the Pliss has a secondary oxygen pack, which is like 6,000 psi oxygen. It will just feed the leak for 30 minutes until you can get back inside the vehicle. So I can't remember exactly what the size we protect for, but that was the design. Yeah.
So do you size them on the ground?
For shuttle, we size them on the ground. For station, we size them at station, and I'll get into that a little bit. That's why we have an old version and a new version, because we needed to have that capability. But that's a good question. Yeah.
Should they drip mold the protective layer for the gloves, the bladder?
Say that one more time.
The drip mold for the bladder glove?
Yes.
Is that just the most effective way to do it, cost-wise?
Versus
Low molding?
Oh, I don't actually know the way it's molded. To be honest, I don't know the exact construction. I believe it's a hard mold, so I don't know what
the astronauts move inside the suit. How are you accounting for reduced and microgravity?
So we do when we can. Obviously, it's a lot easier just to go into the lab and get into a suit, right?
Yeah.
So there's different ways you can do that. We have a pool, right? That's mostly for training. We have the reduced gravity airplane. Now we're using the zero G course plane. So we can do micro G, lunar G, Martian G on that. And we just did that last summer with our new suit. We have also we have various ways of offloading the mass. There's a thing called Argos, and I can't remember the name of the acronym exactly, but basically it's like a whole kind of gimbal system that off-weights your weight. So if you jump up and there's so much pushing, it'll kind of take the weight off and will make you kind of feel like you're in reduced gravity.
So does that take the weight off?
What did you say this was again?
No,
It's a mirror
this
for
is
checking your controls on your chest.
It's more about understanding
So you put it on your wrist and
the
then you
gross
flip open it.
mobility in the
Along with
suit.
your
If you have good
controls.
fit, it's not really a big problem. You're not jostling around. If you have poor fit, then it's probably not very good. It's kind of designed to be a cheaper alternative because zero-G flights are astronomically expensive to do. And you know, Mars, you're fine if you're in microgravity, but Mars has enough of an atmosphere where the thermal protection you use here is specifically for radiation.
How?
Whereas in Mars, conduction dominates, even with that kind of an atmosphere. So we're probably going to have to use something like aerogel. Radiation, pretty well. If you have some unforeseen event, you know, that I think that actually that the ISS is protected by some of the worst stuff. But we have radiation protection in the suit. That's what some of the aluminized mylar helps with. But certainly that's a big, huge issue going forward, like Mars, a trans-Mars mission. I don't think we're... So, specifically for 8 PSI, not really. I mean, we're always trying to improve mobility. And if you had the glove yet, yeah, so when you see the glove, you'll see we're constantly improving it. You know, it's the thing that's been iterated the most in terms of the hardware that's on the suit now. And the difference between 4 and 8 PSI is certainly noticeable, but it's not astronomical in terms of mobility limitations. I mean, you definitely notice it. The reason we do 8 PSI is because if you go from 14.7 atmospheric pressure to 8 PSI, you don't bend. You don't have a bends risk. Whereas now, if you go from 14.7 down to 4.3 PSI, which is where our nominal suit pressure is now, you would get bent. So that's why we have this elaborate pre-breathe protocol where you have to go into a special room in ISS and breathe pure oxygen for like over the night, so you dehydrate your blood, and then you can go EVA. There's a lot of really cool things that are coming out with the integration of fashion and materials and electronics. So e-textiles, being able to carry power and comm through a fabric that is moving and like perhaps stretching. Sensor capability on the suit, self-healing capability on the suit. If you get hit with an asteroid or something, it self-heals. There's some work going on at MIT on a mechanical counterpressure suit that basically will hold, instead of filling the suit with air, it's pushing up against the skin. Anyone know who this is?
Suit?
Wiley Post. Anyone recognize the name Wiley Post?
Yeah.
Okay. This is one of those guys who like should be way more famous than he is in our time. He invented the first pressure suit. He set the record for the first solo flight around the world. He set the record for the fastest flight around the world. He discovered the jet stream. Yet no one's ever heard of it. So he basically made what is the grandfather of pressure suits. He was the first one. 1932, 1933. He was trying to go fly higher and higher altitude so he could get less resistance and fly further with less fuel. And he encountered a physiological limit that he needed to get through. His plane was not good enough. He didn't have enough money to pressurize it, so he decided to pressurize himself. So Apollo, I love Apollo suits because at the time you had all these different companies who were like trying to be the company to go to the moon, right? Had David Clark Company. So 6 weeks before the competition, Hamilton Standard fired their subcontractor, ILC, just because of organizational conflict and they just didn't see eye to eye. The corporate cultures were very different. So upon hearing this, the president of ILC flew down to Houston and asked NASA if they could build a suit in 6 weeks on their own money with their own money for the competition. And NASA said, okay, sure, fine. So they built this suit here, the AX5L, 6 weeks, and delivered it for competition. And that was against the Hamilton Standard AX6H. So Hamilton Standard had just fired LC, then they hired B.F. Goodrich, who made the Mercury suit, as their pressure garment subcontractor. And then David Clark Company. ILC pretty much destroyed everyone. It was a pretty wide margin, and that accounts for the fact that ILC didn't even participate in one of the tests because of the scheduling conflict. It is definitely possible to get too much mass kind of behind you, and so the CG of the suit is definitely something that we think about. In Constellation, we did have specific requirements for where the CG of the suit has to fall. That's usually more of a secondary objective, just because we don't truly understand how much it affects mobility and how to write smart requirements. So we find it's easier just to write mobility requirements, and if they meet the mobility requirements,